All right, all you future PTs out there. Have you ever really stopped to think about the physics behind a perfect rehab exercise? I mean, what really makes it work? Well, it all comes down to kinetics, the science of how forces create and control our movement. Today, we are going to break down the core principles you'll be using every single day in the clinic. So, let's dive in.
Okay, so here's our game plan. We'll kick things off with the absolute engine of all rotation, torque. Then we'll zoom out and see how different forces have to balance each other out to create stability. After that, we'll get practical and apply these ideas directly to human joints, check out the huge role muscles play as our body's motors, and finally, and this is super important, we'll see how this all changes on the fly when we're actually moving.
All right, first up, torque. Seriously, if you're gonna understand movement, you have to understand torque. It's the engine behind every single rotation in the body. Get this, and everything else we talk about today will click into place.
So what in the world is torque? You'll also hear it called a moment of force. Basically, it's the turning effect of a force. The best way to picture it? Think about turning a steering wheel. You're pushing with one hand and pulling with the other, right? Those two equal but opposite forces create what's called a force couple. And what's cool is they cancel each other out in terms of straight line motion, so all you're left with is pure rotation. That pure rotational power, that's torque.
But here's the thing, not all torques are created equal. The amount of turn you can get, how strong that rotational effect is, it really just boils down to two key factors. If you can master these two, you've got the secret to efficient, powerful movement.
First up is the obvious one, the magnitude of the force. How hard is the muscle actually pulling? But, and you've got to hear this, it is not just about raw strength. The second factor is all about leverage, and in biomechanics, we call this the moment arm. Just think of it as the perpendicular distance from the joint's pivot point to where the muscle is pulling. A small force with great leverage can create way more rotation than a massive force with terrible leverage. It's the classic case of working smarter, not just harder. So that idea of leverage leads us perfectly into our next big topic, force systems and equilibrium. We're going to zoom out now from just one torque and look at how the body juggles a whole bunch of forces at once to keep us stable.
You see, in the body, forces almost never work alone. A really common situation is what we call a parallel force system. This is when you have a couple of forces, or more, all acting in the same direction, but hitting different spots on a bone or a limb. This kind of system is what's responsible for both straight-line motion, which we call translatory motion, and the rotational moments we've been talking about.
And these parallel forces, they create different kinds of stress on our bodies. For example, a bending moment. That's when a force causes something to bend, like how gravity is constantly creating a bending moment on your lumbar spine when you're standing. Then there's a torsional moment, which is a twisting force. Think about the crazy twisting stress on a soccer player's tibia when they plant their foot and pivot. As a physio, you have to understand these moments, because when they get to be too much for the tissue to handle, well, that's exactly when injuries happen.
So this brings up a really important question for us as therapists. What happens when all these different forces and torques, gravity pulling down, muscles pulling up, the ground pushing back, what happens when they are all perfectly balanced?
Well, the answer is equilibrium, or in a word, stability. For any object or any patient to be perfectly stable and not move, three things absolutely have to be true. 1, the sum of all the side-to-side forces has to equal 0. 2, the sum of all the up and down forces has to equal 0. And 3, you guessed it, the sum of all the rotational forces, the torques, must also equal 0. If even one of these is out of whack, you're going to get movement.
Okay, that sets us up perfectly for our third section. We're going to take all these physics principles and apply them directly to where it matters for us, the kinetics of human joints, our body's very own axes of motion.
So every synovial joint in your body is built to rotate around an axis, a center of rotation. The easiest way to think about it is like the hinge on a door. And this axis, it's not some imaginary point. It's determined by the actual complex anatomy you see here. All those osteokinematic movements we're always talking about, flexion, extension, abduction, you name it, they're really just a bone rotating around one of these very specific axes.
So if the joints are the axes, the hinges, what's actually providing the force to create the torque? Well, that of course brings us to the stars of the show, the muscles. They are the body's motors, and they are incredibly sophisticated torque producers. Now, to really analyze what a muscle is doing, we can't just say it's strong or weak. That's not specific enough. We need to think of its pull as a force vector.
And that just means it has three key properties we need to care about. Its magnitude, which is just how much force it's generating, its point of application, which is exactly where it attaches to the bone, and its line of action, which is the precise direction of its pull.
And this image here is a fantastic illustration. Let's take the biceps brachii. Its force vector has a very clear line of action, right? It's pulling the forearm up toward the humerus. Now, because that line of pull is a certain distance away from the elbow joint's axis, it creates a flexion torque. And boom, the elbow bends. It is a perfect textbook example of a muscle-generating torque.
Okay, so the body is pretty smart. It has some really clever tricks up its sleeve to make muscles even better at producing torque. And one of the most important of these is something called the anatomic pulley. These are structures, a lot of times they're bones, that actually change the direction of a muscle's pull to give it a better advantage.
Let's look at the classic example, the quadriceps and the patella, your kneecap. If you didn't have a patella, the quad tendon would run super close to the knee's axis of rotation. That would mean a really short moment arm and, honestly, pretty pathetic torque production. But the patella acts like a pulley. It deflects the tendon's line of pull further away from the joint. This makes the moment arm longer, which means the quads can produce way more torque for the same amount of effort. It's a truly brilliant biomechanical advantage.
And that brings us to our final and maybe most important section. We need to understand that these factors aren't static. They change constantly while we move. This is where we get into the dynamic effects of the moment arm, or what I like to call leverage in motion.
So here's the absolute crucial point, the one thing you really need to take away from this. A muscle's leverage isn't fixed. As a joint goes through its range of motion, the muscle's ability to generate torque is constantly changing. It's a dynamic, shifting relationship, and it explains so much of what we see in the clinic every day.
So why? Why does this happen? Well, as the joint angle changes, the angle that the muscle is pulling on the bone also changes, and this directly changes the length of the moment arm, that all-important perpendicular distance from the axis. This means the muscle's leverage is literally changing with every degree of movement.
Let's go back to the knee again. The moment arm for your quads is not the same when you're in a deep squat as it is when your leg is almost straight. In fact, it's at its greatest when the knee is closer to full extension. This is exactly why a patient doing a leg extension on a machine often feels strongest in that last part of the range, and they might really struggle at the very beginning of the lift. Their muscle itself hasn't gotten weaker, but its leverage, its mechanical advantage, has.
And this has a direct effect on the movement itself. Just think back to Newton's laws. A net torque causes angular acceleration, or a change in rotational speed. So as a muscle's torque output changes through a movement, because that moment arm is changing, the speed at which the limb rotates is also going to change. It'll speed up where torque is high and slow down where torque is low.
So if you're going to remember one rule, remember this. A muscle's moment arm, and therefore its ability to produce torque, is at its absolute maximum when its line of pull hits the bone at a perfect 90-degree angle. This is the point of the greatest possible mechanical advantage. It's the sweet spot, and for most muscles, this happens somewhere in the middle of their range of motion.
And that leaves us with a final thought to take with you into the clinic. Now that you understand that a muscle's effectiveness changes through its entire range, how can you use this knowledge? How can you design an exercise, maybe by changing the patient's position or the type of resistance, to specifically challenge a muscle right where its biomechanical leverage is the weakest? That is the real art of applying kinetics to therapy.